we have already practiced using the real example to practice, okay, what's the real analysis would look like if you want to know the change through time. But you, after all this practice, you probably have some questions in your mind. First of all, if I ask you to guess, if we use the 1972, okay, that's the first year, and then we have the annual metrics, and if we do it 19 times, it should become 1991. Do you think it will be the same as the data you have here? Why not? Why not? Or how many of you think it should be the same? No? Should not be the same. Should not be the same, right? How about others? Don't know? You need to pick one.
You mean that only meant for the real situation?
Well, so what I'm trying to compare is that we have the well, 1972, right? 1984. Yeah. All these 3 years are real data, right? Collected from landscape, the satellite images or anything. So we have category 1, 2, 3, 4, 5, and this is the fact. We know it's true. And what we were trying to do is we use this year, these 2 years, and this 12 years difference. So we can calculate the metrics for 12 years. How is this category 1 change to 3, 2 change to 3, things like that. And then we divided that to 1 annual. And then we do it using this data to project 1991. And so you think the projection and the reality will be the same? Raise your hand. You think it will be different? And the reason and the question will be why? Why not the same? What's the potential problem this can have? Because see, we spend so much time to calculate the metrics. It looks like it's promising, and then now none of you think this is real. So what's the problem?
There we go.
Limit? What do you mean limit?
Only maybe 200, so they can bigger than the 200.
What do you mean bigger than 200? I think, okay, try again. I think I know what you want to say. Try again. You can think about other people. Why not the same? What's the potential problem? As long as you can find the problem, that's in this first step, right? Okay.
I think 12 years, the error range will be big. Will be big. So I think something has problem to calculate the data will be different than 2. Yeah.
Okay, so we use the data from here to calculate the 12-year stamp, to calculate the annual stamp, and that should be correct. And then we actually can verify that it should be the same, very close. If you use this to do 12-year metrics, and then it should become 1984. That should be right. There are some minor changes, could be like how many decimal points you are using, or whether you use a cell, and so you need to round up different numbers, and that could make some problem. But if you use the real number, this should be the same. But when you do this, most of you, all of you think will not be the same.
That is even the 12-year situation, but we don't know if every year's situation will be the same.
Okay, that's a very important thing. What else? Is that what you want to say? Not exactly. Okay, then you try yours.
For example, class 1 is more bigger.
Yes, it's larger than expected, right?
I think they have the limit because if we predict maybe 100 years.
Okay, I see where you're going. Okay. Does other people understand him? Well, if you look at the data, right, for class 1 from 1972, it's 37, it becomes 46 or 47, and then it becomes 75. And for our case, there's only 200 cells. Right? So if that's like 12 years, they increase this, 8 years, and 9 years, they increase that. So there must be a limit for you to change. Okay, so that kind of makes sense, but this is actually not a question I'm asking. I'm asking, you already know that, you know that it will go out of bound. We haven't reached that limit yet, but it is different. Why?
The ratio, the numbers change ratio is different because 1 to or up to 5 needs many years, and 5 to 1 would be.
Well, but we already translate everything into annual. For example, okay, let me see if I can draw an idea right. So here is 12 years, right? Here is 9 years. If they are the same, remember in the first place, I asked you why they didn't make it. For example, it should be 12 years. Oh, this is wrong. This is 7 years only. So, yes. Alright, so from here to here is 7 years, right? If just happen that the third year is 1996, then we can use the 12-year stamp. We don't need to calculate the 12 years, the annual ones. We can just do it another time. It will be another 12 years, another 12 years, another 12 years. That's beautiful, right? We don't need all the calculation. But now we know that time is different. That's why we need to calculate the annual one. And then we can do we can predict any years. We don't have a limitation of 12. It's a base. So right now we don't really have that problem because we actually standardize the annual change. So it should be the same, but it's not. Why? Okay. Okay, so actually, the first answer she had is correct. Because things will change every year, likely. And we mathematically would assume they are the same. So you can see the title, the assumption in Markov model, actually is the stationarity. What does that mean? Means they are the same. This transitional probability, what we calculate, it doesn't matter if it's 12 years or an annual. It all comes from here. But what happens next may not follow the previous experience. We assume it will, but it likely will not. So this is the first problem, or the something if you want to make the Markov model works. The first thing is we have to satisfy the stationarity. That means every year it changes. The transitional probability will be the same every year. But the transitional probability will likely change. So if it changes, the result will be different. So that's why, actually, if you look at the data, you know that it will not be the same, right? Because if you do it, you can say that, okay, for 12 years, it increased from 37 to 47. And for the next 7 years, it probably maybe increased less than 10. But it actually increased like 30-something sales, right, for the category 1. So you know that it's not the same. If something changed, that means for the 7 years, even though it is shorter than 12, but the change, like because the category 1 increased, right? That means 2 to 1, 4 to 1, 3 to 1, all those things increase as well. That's why you can see the differences in numbers of 1. The second thing is spatial independence. That means this cell, who is next to me, will actually influence what I become. Not just because right now you will, based on the transitional probability, you know that for category 1, the likelihood for this category change to another category is this, right? There's a probability. But it actually will change based on who is next to me. The third thing is actually related. This spatial independence, we can separate that into 2 parts. They are related. First is the spatial covariance. That means where I stand is a place that actually has some variables that will influence the result. The third one is close. That means it's a neighborhood effect. Think about this. If for the forest, original forest that being cut down, if you want to do this, you need to have a road, right? So if there's a place without a road, the chance that it will change or be cut will be reduced. But if you happen to be by a road, you're probably the first target for people to cut because it's easier. So that's why we need to consider this. The third thing is that the temporal independence is actually talking about the reason she talks about, because could be like El Nino, 声音现象, or could be many other different things, climate change as well. So this will not be the same. So that's why, okay, Markov model looks okay. It's a good way, it's a mathematical way for us to quantify our land use change, but it actually has some drawback or has some things we need to satisfy. So we will talk about each one of them in detail. So the stationarity actually means that for time 0 to 1, 1 to 2, that's a different time span. This is the ratio, the transition that we think they are. But this actually will change. So this is the non-stationarity, which states the transition metrics vary across time period. So that means there's the transition means the rule, right? Where the probability, the chance to change from 1 to 1, 1 to 2, or 1 to 3. That's a rule we have. This rule changes over time. So that's why in reality, the numbers normally will not be the same. So just like the example we had, this transition, if they happen to be 12 years, and if you calculate both of them, you will find that they are different, just like yours. If you try to calculate the annual stamp from 1984 to 1991. First, you need to do it with a 7-year stamp, right? And then you divide everything by 7, and you become annual, and you can compare 2 annual metrics. They will be different. That's why when you use this to project the next time period, it will be different. So that's the main reason. And so if we have data to verify, you will know that very quickly. It will be different. And the spatial independence, things like, if you look at the data, this is a row, right? And then you can see from first year to the second period, for these developments, actually there's like they are growing. It will not appear randomly because it's easier that way, it's more convenient that way, because this landscape change happened because of some process. This process is related to human behavior, and there must be a reason like that. So you can think about if this process is created by animal, could be disturbance, could be competition, could be seed dispersal, to make the change from one period to the second period, then you know that this would not likely to be random. It must follow something. For example, for a certain tree, there's a mother tree here, where you can find this tree in the next 10 years. It won't be random. It will be closer to the mother tree, the more likely you will find that species. So things like that, you will know that they're not independent. Okay. So based on what we do here, actually we will have 2 maps. You can actually using 1972 to do 19 time, and then you can get a projected 1991, which is, okay. You just think about this as a 1991, this is the actual and the projected. So you can actually calculate the differences, and you will know that where the arrow comes from. And there are some things is positive, some places under like a negative arrow. For this means over and under, we just follow the 1, 2, 3, 4, 5. That means for over, that means they actually predict that to be go more than normal. And then for the negative one is that means that the numbers should increase, but the number did not increase. So you can have this kind of projected divided and minus actual, so you will get an arrow back. So you know where the problem is. You will be able to know, okay, this change comes from the differences between 2 time period transition. And then, so you know that, okay, if you have this kind of map, you can compare those 2, you will know that, okay, what actually changed? What's the transition change? And because you have the metrics, right? You have 2 metrics, 2 annual metrics for different 2 periods, you will be able to compare and know where the problem is. But actually, we won't do that. There's actually one other thing. We actually use 200 samples, right, to calculate this. But in reality, there is just like 10,000 of screen, right? So if you do this, it will be more correct than if we get samples. Remember, the arrows propagate, right? The arrow will multiply. If we put something in, if we only pick 20 cells, we can still have a matrix, right? But you will know that this will not be very good. And if we use that to project, of course, it will not be the same. So actually, there are other reasons that things will not be the same. And one other thing that's important, if, just like what Hansen says, there must be a limit. Actually, if you do it, if you have a matrix, and if you assume it's a stationary, that means the change will be the same. If you times 100 times, if you think will become 200.
Maybe.
But there are other categories as well, right? So if the likelihood for all the others, like 2 to 1, 3 to 1, 4 to 1, 5 to 1, is really large. The probability is really large. And if you do it maybe 50 or 100 times, it will become 1. But for other situations, what you can try, actually the reason I want to introduce that little program is that you can actually try. You can just type, okay, this is my starting point. Okay, this is the starting percentage. And then I have a matrix, I input the matrix, and then I do it 5 times. Okay, check. 10 times, check. And if you can do 1,000 times, you will find that a lot of the case, when you go to maybe over 50, it will become constant. It depending on your transitional matrix, but it will actually change and then become stable. But that's just mathematically. But in reality, it will not be that way. But the things I want to point out is that even though mathematically it will work, but when you do it many times to a certain threshold, sometimes in some cases it will become stable. But that's normally not the case in reality. Okay. And so the limitation idea is very good because it will not continue to change. It will become stable at a certain point. Alright, so this is a spatial covariate idea. So, for example, this is a land use. And then we know the transitional probability, but actually the transition will change based on where you are. For example, we can consider this is a climate, different climate or different weather condition. So for different weather conditions, how the land use change might be different. So in this kind of condition, this is the transition. For this kind of the condition, the transition it will be like this, and for this, you can see the transition is different. It's conditioned on certain variables. And this is one variable. You can have multiple variables that actually can have that combined. It's actually more like a reality. You have many factors to determine what this land use will become the next one. And I'll just give you one example. You can think about a landscape that's near the city, or the landscape near the countryside. You know that the transitional probability will be different, right? Because in the city, the more likely the land, the forest or something will become urban or become developed. But in countryside, it may stay as agriculture, as forest for most of the case. So that means for this big landscape, for each different part, the transition rule may be different. So that's the idea of spatial covariance, which also need to consider that. And the other one is neighborhood effect. It's similar to that, but this is actually talking about the one, something next to me. What would that change? And I already give the example of the habitat near the road will most likely to be developed. So something next to you will influence you. Or you can think about if a fire happened here, the ones say near you will most likely to be influenced as well. So this is a neighborhood effect. There are different models, for example, like cellular automata models that can deal with something like this. You can, of course, you need to give them rules. You need to let them know that, okay, well, this is the situation. This is a covariance will be like, and then you will get a more correct projections. One other thing is very important, and this we will talk about, remember the Markov model we talked about is the first order Markov. That means what happened next will be based on what happened before. And what happened in the second year will be depending on the first year, like that. So that's the first order, what that means. But sometimes what happened this year may not only be influenced by the previous years, but could be influenced by the year before, 2 years, 3 years, 4 years. That means here they use this term. It looks like the system has a memory. And so there's a role of history that we need to consider. For example, if you count this, from this to that. So this is an open-end event, and this is the climate. And for this period succession, actually what happened this year may be influenced by something like not only the previous year, but the year before. So it's not stationary. So in this case, if we consider different rules, that we may think that they're actually the Markov relationship should be second order Markov. That means what happened this year will not based on the previous year, but the year before. So that's the second order. And then each cell, you will jump two different years. It could be 3 years, could be 4 years, could be 5 years. And you will see that it could be very complicated. But that's an assumption that we need to consider if we want to use the first order Markov, and to make sure that there's no effect of history, and so we will have a better idea for that. And the other thing is disturbance. We assume nothing special changed. All the rules follow certain things, but actually there are sometimes, a lot of the time, there are disturbance happens, or it could be human related, it could be natural. Like a typhoon comes, of course, it will change. So you will see that the disturbance may have a physical constraint. That means if the fire here, this is one species, it's actually fire resistant. That species is actually fire prone, not like pine. Pine tree, they will have a lot of pine needles, and if it gets fires, it will get disturbed. We will get a fire very soon, but the other species may not. So there's physical constraint, there's a spatial covariance. And maybe there's spread contingency, just like the neighborhood that if I have a disturbance, will not continue or not. And the disturbance may have a lag in time after previous event. So that's the one I talked about, the time lag. It could be second order or probably the third order. And disturbances are often stochastic. Remember the term? Stochastic models. That means this model, every time there is something different. So it means you cannot predict where it will happen. And that's why, in reality, that's why it will not be as easy as to predict, because there are many things randomly to discover. So that's why we actually will both change it through from the land use change models, Markov model, to land use disturbance succession model. And because the Markov model is just a very simple concept, and it's easy to calculate, but it has to meet a lot of assumptions. But it's much easier, actually. I think that's a very good tool for students to understand what it means. But in reality, there's succession and there's disturbance. After the disturbance, the tree will grow, right, by itself. Just like what we are doing here for our land, the class 1, 2, 3, 4, 5. It's all forest, but it's managed or modified by human beings. But after disturbance, if there's no human impact, you should expect the forest to develop from grass to shrub to trees and to large trees. It will progress like that. And that's why this model is very important to the real landscape, the projection. And we will introduce a little bit, give some example of landscape disturbance succession model. And then we will introduce the neutral model next week as well, and it's our last lecture. And in 2 weeks from now, we will have a midterm finally. And what we will do is that I will give you several questions. Most of them will be open questions. So I'll just ask you what's the factors we need to consider, what's your ideas about this and that concept. And so basically it's of course in English, right? So there actually one time in this kind of setting, I didn't specify, but when I get the test out to students, when I get the test back, some of them actually reply in Chinese. So I was like, what happened? I actually don't think I need to say it, but because this is a class taught in English, so your answer should be the English as well. So I will allow you to use your dictionary. Okay, so I don't want the language becomes a problem, but you should still have the concept, and then you try to practice and to reply that in English. Okay?